Welcome to phiVis, the Philosophy of Vision Science workshop. My name is Kevin Landy, and I organize this event alongside Chaz Firestone. And I'm an assistant professor of philosophy at York University in Toronto, where I'm also a member of the Center for Vision Research. And my work's in philosophy of vision science, which means in this area, philosophers try to ask basic questions about the nature of perception, the mind, and knowledge, by thinking deeply about the results and experimental paradigms of the vision sciences. So when we started this event 4 years ago, our initial thought was that a lot of philosophers were eager to attend VSS. We thought that because I was super eager to attend VSS. In talking to lots of scientists, we also had a sense that some were really enthusiastic about having philosophical conversations and would love to have more opportunities to do that. And we've been sort of blown away by the reactions, both personally in terms of attendance and also in terms of social media and email responses. People saying that they've really enjoyed the event, that it's one of their favorite discussions, and even turning down kayak trips to see manatees to attend phiVis, which we take no responsibility for. It's also rewarding to see that the event is now having some small part in new and exciting work, both coming out in philosophy and psychology. Wayne Wu, a previous participant in a new TICS article, acknowledges the phiVis satellite. In an important new book, Ned Block acknowledges an unnamed satellite event at VSS. And in a forthcoming BBS article on attention, Ruth Rosenholtz acknowledges phiVSS. So branding is not our strongest suit, but we have other advantages. So none of this is to say that communication across fields is always smooth. We're often driven by slightly different questions and priorities, and can take a lot of work before we feel like we're on the same page. The goal of phiVis is to get us on the same page and to find the places where the conversation can be illuminating, but also just fun. So I'm going to hand it over to Chaz to say a few things before we kick it off.
Thanks, Kevin. My name is Chaz Firestone. I'm an associate professor of psychological and brain sciences at Johns Hopkins, but I also teach and advise students in our philosophy department. And in fact, several members of our lab actually have degrees in philosophy, sometimes graduate degrees. And I've been able to see really firsthand the value that philosophy can bring to scientific investigation. Having one foot in the door of philosophy has really helped me appreciate the care and attention to detail that philosophers bring to their engagement with the experimental literature. Philosophers basically cultivate deep, careful thinking as their intellectual superpower in ways that I know our field can benefit from, if only because I know that our own work in my lab has benefited from it. And that's true not only as researchers running experiments, but also just as people trying to figure out how the mind works and just ask and answer interesting questions together. Now, at the same time, it's true that our two fields differ in many ways. Like Kevin said, we don't always have quite the same language or concepts. And so part of our goal with this workshop is not only to have these conversations, but also to learn how to have them better. And we think there's really no better place to do this than the center of the vision science universe, which is, of course, VSS. So it's time to get to it. I'll turn things over back to Kevin, who's going to tell us a little bit about the schedule for the next 2 hours.
Just real briefly, we're going to have 3 20-minute talks from philosophers of vision. Each talk is going to be followed by a brief discussion from a vision scientist. And after each round of comments, we'll have a bit of time for a question or two. There's a microphone up front if you'd like to line up to ask a question.
And so we're not going to waste any more time. We're just going to go right to our first talk. So our first speaker is Ian Phillips, who is the Bloomberg Distinguished Professor of Philosophy and of Psychological and Brain Sciences at Johns Hopkins. And his talk will be called From Unintentional Blindness to Blind Sight, Degraded Awareness Should Be Our Default Hypothesis. Take it away, Ian.
Okay, so firstly, can everyone hear me actually? Okay, so firstly, a huge thank you to Kevin and Chaz for creating this event and for the invitation to come this year. And also to Jeremy Wolf, who so kindly agreed to give some comments after this talk, which I'm really looking forward to. So this event, phiVis, raises a natural question, right? What is the relationship between philosophy and vision science? And I don't actually think there's a single answer to that question, but I want to begin with just one possible conception. And this conception is one kind of famously associated or articulated by the philosopher Wilfrid Sellars, who proposes that the principal aim of philosophy is to try at least to reconcile what he calls the manifest image of kind of common sense or the world as we find ourselves encountering it with what he calls the scientific image, namely the picture of the world that is delivered by scientific inquiry. So today I want to think about a really old question about the relationship between attention and consciousness. And in line with sort of Sellarsian methodology, I want to think first about what the manifest image of the relationship between those two things is. So here, Bernie Bars gives a very nice, I think, articulation. He says, common sense makes a fundamental distinction between attention and consciousness. People conceive of attention as more selective than consciousness. And in line with that, Chris Moll, philosopher, says, according to common sense psychology, one does not pay attention to all the things one is conscious of. Okay, but what about vision science? What about the scientific image? Well, one of the most celebrated paradigms in all of vision science and probably all of psychology is inattentional blindness. And inattentional blindness has been studied in a host of different ways over the years, but at its core is the finding that naive observers whose attention is occupied by a demanding task very often miss highly salient stimuli, which they are not expecting. Okay, so most famously, tasked with counting the passes of a basketball, right, between players here wearing black shirts, half or more of naive observers miss a woman in a gorilla suit parading right in front of them for several seconds. You should be along in a second, there she is. Okay, on the basis of their seminal studies of inattentional blindness, Mack and Rock concluded basically that the scientific image of the relationship between attention and consciousness is just incompatible with the common sense manifest image. So in defining the term inattentional blindness, Rock and colleagues write that one striking unexpected finding is that without attention, many subjects have no awareness at all of the stimulus object. And as they ultimately conclude in their famous monograph, there is no conscious perception without attention. And many others, philosophers and scientists alike, have kind of followed suit and interpreted IB data in similar terms. So here's the philosopher Peter Carruthers. As inattentional blindness demonstrates, one can have one's eyes focused on an object or event without seeing it at all. It is attention to a stimulus that produces conscious experience. And I won't read these out, but these quotations from Jesse Prince and Stan DeHaan say very much the same thing, right? They're all saying, in effect, that inattentional blindness is a direct demonstration that in the absence of attention, there's no awareness. So the first thing I want to do in this talk is to kind of summarize some recent work I've been doing, which helps, I think, in the task of reconciliation. And it's actually empirical work, but I take it to be driven by a kind of a philosophical motivation. And this is joint work with someone you're very familiar with. In fact, two people I'm sure you're very familiar with. Howard Eagerth has turned up in like tons and tons of presentations at this conference already. But the person who's really done the hard work is a graduate student of ours, or in fact, recent graduate student of ours. She's now Dr. Natka, who's presented some of this work at VSS at this conference. So a special thanks to Michaela for all her work on this project. Okay, so our work exploits a very classic task designed by Mack and Rock in their studies of IB. And in this task, subjects are asked to fixate on a circle and then to press the space bar when they're ready. And then a cross appears like it just did, and subjects have to report which arm is longer. So here's the second trial, and a third trial, and the fourth trial. Okay, and so perhaps some of you noticed, you're hardly naive, that something unexpected did appear on that screen, a black circle, a black triangle in the center of the display. Okay, and then subjects are asked the traditional question in this literature, did you notice anything unusual on that last trial, which wasn't there on previous trials? And the central finding in the literature, right, is that many subjects say no. The exact number, of course, depends on the parameters of the experiment, but many subjects say no, they didn't notice anything unusual, despite a highly salient stimulus being presented right in front of their eyes. And that sizable group of non-noticers is the basis of the claim, in effect, that without attention, you don't have consciousness, you don't have awareness. But there's, of course, an important methodological question that arises here. Namely that the basis of the judgment that subjects aren't aware of that stimulus is just that they've told you, no, they didn't notice anything unusual in relation to this question. And you might well worry that this measure of awareness wasn't adequate. So to press that familiar methodological question, our studies did 4 things, which in combination, I think are unique in the inattentional blindness literature. So the first thing we did was to add some forced choice or forced response questions about what appeared after the yes/no question had been asked. And the point of that is to assess objective residual sensitivity in subjects, even those who are classified traditionally as inattentionally blind. Second thing we did is add absent trials, so trials where there's no unexpected stimulus, but we still ask subjects whether they notice anything unusual anyway. And the point of that is to get a false alarm rate to calculate response bias. The third thing we did is pull together all the single trials, and in inattentional blindness, you only get 1 trial per participant before they're not naive anymore, into a kind of super subject to allow signal detection analysis. And finally, we, or rather Michaela, ran a huge number of subjects. So across all the experiments we did, which I won't tell you all about, we ran something like 25,000 subjects. And obviously the point of that is to do some rigorous statistics. So let me just give you a flavor of what we did by looking at a couple of our experiments. So the first one explored sensitivity to location in a version of this kind of modified Mac and Rock task. And the task looked exactly like the one I showed you before, except instead of a black triangle, we presented subjects either with a red line to one side of the screen or a red line on the other side of the screen. Okay, so after that critical trial where the stimulus has appeared, we ask subjects this standard question: did you notice anything unusual or not? But then we follow it up with a question about a forced choice question about location. So we say, in fact, the last trial you just saw did contain 1 extra element, a vertical line on either the left or the right of the box. What side do you think it appeared on? And to jump straight to the data, and this is data just for subjects who said they didn't notice anything unusual, so those who are supposedly inattentionally blind, we found that they performed well above chance on this forced choice question. So 64% of the inattentionally blind non-noticers correctly reported the location of the line. And we can look at that in terms of D prime too. And so the inattentionally blind group of non-noticers exhibited a visual sensitivity of about 0.5. So not amazing, but definitely significantly above 0. Of course, much worse than the subjects who said yes, where D prime was something like 2.7. Okay, we also looked at color discrimination in another experiment. And here too, just by making the line red or blue and asking subjects what color it was. And here too, subjects who were in the non-noticing inattentionally blind group demonstrated significant visual sensitivity. Their D prime is about 0.4. And we also looked, just to generalize this, at dynamic displays. So to see whether the same pattern occurred in this kind of setup. So this is a classic design from Steve Most and colleagues, in which subjects fixate on that central checkerboard, and then they're asked to count the number of times the white squares bounce off the walls of this square. And in the midst of doing this task, on the critical trial, an unexpected object, here a green triangle, traverses the screen for 5 seconds. And in our studies, this triangle could be, well, this unexpected object could be a triangle or a circle. It could be green or orange. It could be on the left or the right, and it could move up or down. So again, we show subjects this display, ask them, did you notice something unusual? And then follow up with some forced choice and forced response questions. And here's what we found. Again, visual sensitivity for color and shape was significantly above chance in the non-noticers. But interestingly, perhaps not so surprisingly, given how much location kind of noise there is in these displays, it wasn't above chance for location. Okay, but overall, what we find is that subjects who are classically classified as inattentionally blind exhibit significant visual sensitivity to a range of different features in inattentional blindness. And notice these are all low-level features, so these results are quite consistent with it being the case, perhaps, that inattention abolishes high-level features awareness, but certainly there is visual sensitivity for these kinds of features. Okay, so let's just pause now and ask, what's the most natural interpretation of that data? What I want to suggest is that the most natural interpretation is that perceptual awareness is a graded phenomenon, and that what attention is doing is not turning off, inattention is doing is not turning off awareness, but rather degrading it in a way without abolishing it entirely. So subjects are left with something like a partial percept or a degraded percept of the relevant object. And this viewpoint, I think, is completely consistent with the manifest image So the manifest image of the relationship between attention and awareness is not that attention has no effect on our experience at all. It's perfectly consistent with attention boosting or altering or modulating various aspects of our visual experience. The point is that the manifest image claims or holds, I suggest, that there is conscious awareness outside of attention. And that's what these results seem consistent. This interpretation is certainly suggesting are consistent with. Okay, but there's a residual question which naturally arises. Why, if subjects do have degraded awareness of these stimuli, are they saying no, they don't notice anything? And here's where the absent trials I mentioned, I think, are revealing. So these trials, right, are trials where nothing unexpected is appearing, but we're asking subjects, did you notice anything unusual or not? And the point of these is to introduce a false alarm rate with which to measure response bias. And so in line with our predictions, in all the different experiments, and more actually than just these that we've run, in which we've included absent trials, we found a significant conservative bias. So that's a tendency towards saying no in relation to that question, did you notice something unusual, independent of whether it's actually a stimulus being presented or not. And what I want to suggest about this bias is that it perhaps helps explain why subjects are saying no, even though they do have degraded awareness, for perhaps a whole range of reasons. So here are just some kind of speculative things that might be going on in a subject's head as they confront our displays. So maybe they think, well, I did notice something, but I don't know what unusual means. It was just a line, so perhaps that's not unusual enough to report. Here's, I think, a more likely thing they might think. They might just think, I don't really know. I think I might have noticed something, but I have pretty low confidence in it, and I want to play it safe, so I'll say no. You know, another thing a subject might say is, in their head, as it were, I noticed something, but I couldn't really tell you what it was. And I'm sure this person who's asking me these questions is going to want to know what it was if I say I saw it. So I'm going to avoid that question and say no. Okay, you can do this for a long time and come up with other explanations. But the key point here is that it's quite consistent, I think, with subjects having degraded awareness that they would answer a question like this in a negative for many reasons. Okay, so does this mean we've reconciled the scientific image of attention and consciousness with the manifest image? Well, not so fast, many people will say, because there's an alternative interpretation of our data, which is critical to consider. And this interpretation holds that all this performance is perception or perceptual performance in the absence of awareness. So this doesn't tell us anything about the manifest image of consciousness and attention. And this idea of perception and perception-based performance in the absence of awareness, again, I want to suggest kind of represents a clash of manifest and scientific images, which immediately should get the philosopher interested. So why do I say that? Well, I want to suggest that the manifest image of perception simply takes it to be a way of being conscious of things. So not that dictionaries are super reliable, but this is how the Cambridge Dictionary defines seeing. It's just to be conscious of what is around you by using your eyes. So to stick with Cambridge, here's the famous Cambridge philosopher G. Moore. In A Defense of Common Sense, he writes, the fact that I'm seeing something is a fact with regard to a specific way of being conscious. Okay, so that I want to suggest is something like our manifest image of seeing. It's a mode of consciousness. But again, work in vision science, actually a huge amount of work in vision science, but let me just highlight one celebrated phenomenon, namely the phenomenon of blind sight, has been taken to overthrow this manifest image. So blind sight is the phenomenon of substantially preserved visual function, allegedly operating in the complete absence of awareness following lesions to primary visual cortex. So here on the left, you can see Larry Weisskranz with the patient GY performing discriminations in his right hemifield, his right blind field, which is being caused by a lesion to his left primary visual cortex. So he can discriminate orientation and motion and detect stimuli in that field well above chance, despite saying he has no awareness. And on the right here, you can see Beatrice de Gelder and her patient TN, who has a bilateral lesion to his primary visual cortices. And he's walking down a corridor unaided, navigating these obstacles despite saying he's doing it. Okay. Many have taken blind sight to show that even goal-directed intentional responding in a visual task just isn't clear evidence. So here's Weisskranz. A point that emerges transparently from the phenomenon of blind sight is that one cannot draw any conclusions about whether a subject is or is not consciously aware of events simply by studying how good his performance is. And again, more quotations, which I won't read out, saying pretty much the same thing from Pat Church and here and Chris Frith and colleagues. Instead, the dominant view that has arisen from phenomena like blind sight is that we need to recognize the existence of unconscious vision or unconscious perception. So by that, I mean not merely unconscious processing, which I kind of want to think of as an uncontroversial fact that's been established by science and doesn't, I think, conflict with anything in the manifest image, but unconscious signal that's available to guide intentional responses, and so should, for that reason, count as genuine perception. Okay, so I've got a few minutes left, and in those few minutes, I want to sort of suggest that we've perhaps been bewitched by this phenomenon of blind sight and maybe other findings also. So the first crucial point to make here is that just as in inattentional blindness, the lack of awareness in blind sight is being measured by simply asking subjects, are they aware of anything or not, in various different ways, but still with the same basic pattern. And again, there's a serious concern that arises there about how we should understand the adequacy of that measure of awareness. Here, the second thing, and this is again comparable, although much more extreme in blind sight, comparable with our results in attentional blindness, is that subjects with blind sight tend to adopt extremely conservative criteria in relation to yes/no tasks. So here, highlighted in red, is GY's criterion. It's about 2 on average in a yes/no detection task. And this is data from Paul Azzopardi and Alan Cowie. So GY is adopting a very conservative criterion in these tasks. For those of you who are familiar with this work, I should say, because I'm sort of drawing on Azzopardi and Cowie's work, that their paper here in the 98 paper seemed to establish an important dissociation between forced choice and yes/no tasks in respect of the objective measure D prime. But although that looked like it might show that there was unconscious signal available to forced choice responding that wasn't available to yes/no, perhaps conscious responding. In fact, later work suggests this is actually a kind of an artifact of the fact that GY's criterion is unstable in specific relation to static stimuli. And that jitter of his criterion, or that movement of his criterion across trials, artifactually lowers the measure of D prime in yes/no tasks, but not in forced choice tasks. So for that view, have a look at Azzopardi and Cowie's later paper from 2001. Okay, but the main thing I want to take away from these 2 points, we're measuring awareness by looking at how subjects say respond to a yes/no question, and the fact that they're very conservatively biased in relation to it suggests, right, that we should take seriously that there's degraded vision in blind sight that's not being reported under standard forms of questioning. Okay, and a prediction of that proposal is that we ought to be able to find reports of awareness if we can get the subject to move their criteria to a more liberal place. And I just want to end by showing you a few places where I think that's happening, kind of as a teaser. So here's a study I really like, or just a part of a paper I really like from Sturg and Barth. And they basically flash very bright white stimulus in various locations in GY's blind field and ask him to press a button when he sees something. And this is what you get. It's kind of standard perimetry for GY. Lots of negative black responses, cases where the button isn't pressed in his blind field. Looks like he's completely blind. Okay, but then they just shift the question from press when you're aware of something with exactly the same stimuli to the question press when you see something to press when you're aware of something. So small change in the question, one you might think would induce a more liberal response bias, and indeed this is what happens. Suddenly there's a huge number of yes responses that weren't present in the original case. And so I think if you just saw that, you would not think the subject is who's straightforwardly blind. Second piece of evidence, this comes from looking at blind sight patients and giving them more nuanced response options. So a study was done by Chiara Mazzi and colleagues where they gave a blind-sighted patient SL a whole bunch of different tasks. And in the first block of these tasks, gave her the option to say every trial that whether she did it on the basis of seeing or on the basis of guessing. And this is what they found. The black bars are where it's black, it's guessed, and where it's sort of light, it's seen. And so in these orientation, color, and contrast discrimination tasks, you can see that most of the time she said, oh, I was just guessing, didn't see. And in some small amount of the contrast, and in the motion cases, she's saying that she did see something. But then they repeated all these discrimination tasks with a more nuanced bunch of responses. So 0 for no awareness, 1 for weak awareness, 2 for almost clear awareness, and 3 for clear awareness. And this is what they found. They found that the black actually collapsed weak awareness and no awareness. And when the seen responses corresponded to almost clear and clear experience. So it turns out that the response, no, I just guessed, I didn't say anything, actually collapses across weak experience and no experience. And they found no evidence of preserved visual function for zeros, i.e. no experience, only where there was actually weak experience. Okay, very nearly there. Just one final anecdotal thought about blind sight, and then I'll wrap up. The final anecdotal thought is that there was a study done by Zeki and Fish, in which the patient GY was being asked to report his awareness on a scale from 1 to 4. And in a particular low contrast block, he says, my awareness on this trial should be -1 or -2. And I think you immediately reflect on that and think, well, it must be that his ones, i.e. his ones for no experience, cannot be absolute 0 of experience, that he's got more to go, as it were. So again, that suggests that, you know, we can't take these reports at face value. Okay, for much more in-depth discussion, let me advertise a paper of mine which tries to defend this view at great length, but I realize I'm over time. So to wrap up, I think many people have been convinced that by blind sight and other things, that rich unconscious perception is something we need to recognize. But the data from blind sight, I want to suggest, are actually perfectly consistent with the hypothesis in which what in blind sight, the lesions to V1 do is degrade, perhaps radically, perhaps qualitatively, the nature of conscious vision, but performance is still in fact based in conscious vision. So that means we've got no reason to resist a natural interpretation of our data on inattentional blindness, namely that inattention degrades without abolishing visual awareness. And so no reason to reject a manifest image of consciousness and attention being related in the way that I set out at the start. So just one final thought, and I really don't need to convince anyone here of this. Vision is a complex thing. There's like thousands of people here every year trying to figure out its complexities. So we really shouldn't expect different interventions to degrade. We should really expect different interventions to degrade it in a whole myriad of ways. And we should not expect, on the other hand, simple reports, did you see, didn't you see, to capture that complexity and that diversity. And if we do, we're liable to be misled. Okay, thanks very much for listening.
All right, so next up, we're going to have comments from Jeremy Wolf, who is professor of ophthalmology and radiology at Harvard Medical School. So Jeremy's going to share some thoughts about Ian's talk, and then we'll have a Q&A where you can ask them about anything.
So that I like that as a title. Ian was good enough to share his slides with me, but I didn't want to do the thing where you say, thank you very much for your fascinating talk. Now let me give an extra VSS talk about what I think is cool. So I threw a few demos onto slides in case they would be useful. And then I took extensive notes, and I put the wrong slides on there, but not entirely the wrong slides. So let me try. How do I navigate here? Where'd my mouse go? There's my mouse. Oh, I don't want to do that. I want to slide this. Oh, that's how that. Oh, no, that's not good. I'm going to give away all my escape. Go. Yes, thank you very much. All right, I think I will play with that slide in a minute. No, I'll play with it now. Yeah, I don't show all my slides. So I think there are sort of three stories at play here. There's the sort of common sense view that the people who don't go to VSS would have. I open my eyes, stuff comes in, I see the truth. Now you show me that I didn't see that gorilla, and I'm completely buffalo. There's the, we could call it the sort of the Mac and Rock kind of version that Ian did talk about, that I see the world, there's the world, it comes into the visual system. There's this attentional bottleneck. And if it doesn't get through that bottleneck, it doesn't get up here to awareness, because only with attention do I see anything. That's a view that, as Ian said, has been propagated around these sort of worlds at various times. But there's another view, which I think is almost sort of what Ian was arguing for, but certainly would be consistent. Well, I better not say it certainly would be consistent with Roosevelt's going to hit me later. But there's the idea that vision comes in, massively parallel stuff happens. It's limited by various things and maybe degraded. And as a result, under the right circumstances, the gorilla somehow is degraded in visual awareness, and I don't see it. I think that for present purposes, what I'd like to do is argue against the idea that it necessarily needs to be degraded, that there's anything that's actually degraded. I think that the naive folks have a point when they say, I open my eyes, I see the world, it looks fine. I mean, you guys all look pretty good. A few of you are kind of degraded, but that's a separate problem. I think we are partly in a bit of a quandary because we miss the possibility that both of these things are true, that there are two ways to get to visual awareness. One of them with a severe attentional bottleneck, and another that is subject to various other constraints, but is giving you something everywhere in the field. And that if you don't get yourself tied down to the notion that you need to explain how we go from point A to point B by only one route, that a number of these problems become less extreme. I'm counting on Kevin to wave when I should shut up. Right, okay, good. All right, now we'll go the other direction in slide land. Because, so let me try to illustrate something like, it's not quite the naive view, but somewhere in there. What I'm going to do is I'm going to flash up I'm going to fling open these curtains. The reason I'm going to fling open these curtains, I should say, is in honor of the philosopher Condillac, who has a lovely piece about sort of pre-attentive vision or something, where he imagines going to a chateau at night, and the next morning his host flings open the curtains, and the philosopher Condillac says, "What would I see when you fling open those curtains?" So I brought some curtains. 2 minutes. I'll fling them quickly. Ready? Whoops. Fling. Yes, good. Quite apart from the gorilla, what did you see? Yeah, I got it. They're all muttering here. Yeah, thank you. Pluses, you saw some X's, you saw some colors. What were the colors? Yeah, good. Okay. For present purposes, I would argue that you didn't think that it was quick, but it wasn't particularly like degraded or blurry or icky or something like that. But if I ask you, which plus did you see? The one with green vertical or red vertical part? How many vote it was the green verticals? How many vote it was the red verticals? How many vote it was neither because it was just a gorilla? How many vote that basically you didn't know, even though you know there are red and green pluses? So the answer actually turns out to be both. But this is a classic binding demo. You cannot decide which item was actually there without attending to that item. But I don't think it means that when that thing came up there, that it was degraded as a perceptual experience by attention. If the real the spotlight of attention people were right, you pay attention to this and all the rest of it would somehow disappear. That clearly doesn't happen. This is not a quick, simple explanation of the gorilla, but I do think it's an argument that your visual awareness is not particularly degraded, even under cases of typical inattention, but important aspects of your visual processing are absent. I should probably stop, right? I should definitely stop. Yes, okay, that's it. Okay, thank you. Okay.
We now have a few minutes for Q&A. You can ask questions of Ian or Jeremy or the room, however you like.
I do avoid stepping on people.
Is that mic on? No, chat.
Ian, can I fight back a little bit and represent inattentional blindness?
Yeah.
I want to suggest a difference, and I think actually you talked in the end about the most natural interpretation of your results. I want to suggest what I think might be a more natural interpretation. And it has to do with the relationships between the population, the super subjects in your strategy, and the individual people. There's always been a real question about what that relationship is. When you have 30% inattentional blindness, the question, does everybody experience inattentional blindness 30% of the time, or is it 30% of people who experience it? But by lumping everyone together in a super subject, you have to draw conclusions about the entire population, and your conclusion is that everybody the population as a whole experiences degraded awareness. But the other possibility, of course, is that some people, it's always been a minority, like around 30%, and maybe what you've found is it's even more of a minority. Some people have a high criterion, some people have a low criterion, and some people are really true that they see nothing. That if you give them immediate report instructions, as some of us have done, they won't press the key. You put them in a driving simulator and you don't ask them anything, but you look to see if they run over the little girl who runs across the street, they run her over. They really don't see anything. And you can't see that in a super subject. But like, one thing I want to focus on is that when you debrief subjects in person, like in inattentional blindness, you're totally right on the screen. Some people say, oh yeah, okay. A bunch of other subjects will say like, no, like this is the experiment, isn't it? You're trying to convince me that this happened. There's no way I'm falling for that. Like they'll go to the wall and say they had absolutely no percept at all. So the most natural interpretation I want to push back is suggest that some of the subjects, you're right, had a overly conservative criterion and really did experience something. But still, a fascinating minority of subjects are 100% inattentionally blind. What do you think?
So great, thanks, Brian. I mean, I don't think there's anything straightforward in our data which could rule that out. And part of the problem here is like, we're forced, if we want to do kind of signal detection type of things, to lump everyone together. One thing we did do, which might speak to what you're saying, is looked at confidence. We had one experiment where we did confidence ratings after the yes, no. And then we just looked at the subjects who said, no, I didn't see anything unusual. And I'm really high confident I didn't. And even in those, we found that D prime was significantly above 0.
Population.
In the population.
All right, I would leap to Ian's defense and say that in the problem with classic inattentional blindness paradigms, you get one trial per subject, and so you can't know. But there are plenty of paradigms where people miss perfectly obvious things that are right in front of their eyes, and everybody does that. There's no, in even just standard visual search tasks, there's no task where there are some people who miss all of the targets and some people who miss none of them. It just doesn't happen. So it might happen to us.
Yeah, thanks so much. So I guess I have a question about the nature of the defaultness of the hypothesis. So you put a lot of weight on blind citations, with GY in particular. But I was thinking there are other cases of reported unconscious perception, such as with the like subjects who have lesions to the ventral stream seem to be able to perform actions perfectly well, but they don't report any conscious experience. So why rule out the unconscious perception hypothesis just on the basis of the patient GUI? Are you thinking that that's going to extend the arguments for GUI are going to extend straightforwardly to the arguments against patients like DF?
Yeah, thanks. I mean, the simple answer is I had 20 minutes and I went over even that. I mean, I think it's really important to, in every single case, to look at the situation really rigorously. Personally, I'm not convinced that what's going on in DF should be thought about as an unconscious stream of information that's guiding their actions, as opposed to all sorts of complications with, are they doing the particular action, like the posting action, on the basis of information they do have? It's just not the information that you kind of naturally expect them to be using to do that task. And so there's a huge story to be told there. But I totally agree, we need to take every case seriously and look at it.
We have time for one more question. Anina, if you'd like to ask a question, or Michael, Michael, you'll be first in line in the next one.
It was first, but I also want to encourage all the women to stand up and ask a question, so I'm going to be brave and do it. Doesn't it all come down to your definition of awareness, though? I mean, I'm happy to say that, yes, you, like, there's lots of evidence that we have above chance, above deeper and above chance in all of those situations, but I would just like to call it unconscious processing, which we know happen. And so really, I think we're quibbling about, we're not quibbling, it's a big question, right? But I want to see what's your definition of awareness. If you define awareness as d prime above zero, then yes, you've got evidence of awareness without attention. But if I define awareness as, or someone else wants to define awareness as when you know that you've seen something, then a d prime above zero doesn't give you that.
Yeah, I mean, I don't want it to be about definitions. One thing I think is that D prime is more than just unconscious processing. What it reflects, at least when the subject that's being characterized by that statistic is a human being, and the kind of discriminative responding that it characterizes is them making voluntary responses to a question, is them themselves having information they can use to perform a task. And that seems to me much closer and interesting ways to evidence of consciousness than merely stuff being processed in part of the visual cortex site, which I definitely think can happen without consciousness, but much more to say. Thanks.
All right, thanks, Ian, and thanks, Jeremy. Our second speaker today is Rosa Cao, who is Assistant Professor of Philosophy at Stanford University, and will be talking about comparing brains and models, what matters for similarity.
Okay, I've never used a Mac before, so wish me luck. Okay, so I'm going to be talking about similarity, which is an old philosophical question with, deep implications for metaphysics and universals and all kinds of philosophical waters that are usually way too deep for me to wade into. But it turns out it also matters. Okay, is this better? Yeah. Great. So it turns out that similarity, in addition to mattering for all these deep metaphysical questions, also matters for a very practical question of thinking about models and brains and models of brains and how we should assess those models. So this is VSS, and I was told to use pictures. So I'll just open with a warm-up question. How do pictures work? Right. So, like, in virtue of what do they manage to represent the objects portrayed in them? So what is this a picture of? Okay, how can you tell? It looks familiar, they're landmarks. Okay, so it turns out there's a huge literature on this, very sophisticated answers. But one sort of obvious thought is that pictures resemble what they're pictures of. So, like, the shapes are the same as the shapes of the things that they are pictures of. The colors are the same. The arrangements are the same. That there's something in common there, that they're similar to each other in some relevant respect. Okay, what about this picture? Anyone know what that is?
No.
Yeah, Yeah, also St. Pete's Beach, or at least that's what the caption said on the website where I downloaded it. But, you know, would you give the same answer here, right? How could you tell? Did you guess?
Similarity.
Similarity again, okay, cool. So what now are the properties that are the same between this and what it actually looks like outside? There's a C, okay, so there are objects that are, but like, how can you tell that that's a C? Right, like, why is that not just a pool of paint? Okay, you have some priors about what's going on? Okay, and like the sky looks totally different. Like, why would you even think those were the same kind of thing? There's like no contours up there. There's so many edges and like bright colors here. Okay, I'm asking stupid questions. I'll move on. But I think you get the idea. What's this a picture? Okay, so I'm not going to solve the problem of depiction here, but I'll ask a different but also probably annoying question. So which of these pictures are more similar to each other? The first two are more similar. Everyone agree? Okay, who thinks these two are more similar? Okay, and who thinks these two are more similar? Oh, interesting. Okay, so why? Why are the second two more similar? Yeah, the style, the colors. Right, okay, so
I think the first two have different style, like the first one doesn't have like clear symbol, but the second one has a bit of like plain symbolism.
yeah, so I'm gonna say the uncontroversial thing, I hope, which is that reasonable people could disagree about this. Right? It's, you know, in some sense, the first two look more like each other. In another sense, maybe the second two look more like each other. And you might think, oh, that's just a property of what it is for things to be similar to each other. Right? They're going to be similar in some respects and different in other respects. Right? Uncontroversial. Does anyone disagree with that? Okay, great. So that seems fine if we're just talking about pictures. Nothing much hangs on this question. But you might worry that if we want to use the idea of similarity for science, that we would like our verdicts about what's similar and what's more similar and what's less similar to be objective. Right? We want to be able to agree on it and to agree on it for principled reasons. Okay, so it's because of issues like this that similarity has gotten a bit of a bad rap in philosophy. So I don't know if you can read that quote, but I'll just give you the general idea. So Quine famously called it logically repugnant. Goodman says, for any three objects, there will always be some respect in which two of the objects resemble each other more than the third. If we have a green square, a red square, and a red circle, there's no obvious pair whose members are more similar to each other than the third. And that's with something with two properties. Right? So now imagine we're thinking about brains and we're thinking about models. Now there are many, many. How are we going to operationalize assessments of similarity so that we can evaluate models based on how good they are, how similar they are to the thing that they're supposed to be models of? Okay, so just backing up a little bit, this is sort of assuming a kind of strategy of model-based science where you have a model system, you have a target system. In our case, maybe it's the visual system, maybe it's the brain, but in principle, it could be anything. And you have a model system that's simpler to understand in some ways. And then you understand things about your model system. And then you go and apply those to your target system because you think that they are similar enough in the relevant respects. And I think there's this background thought that the more your model system resembles the target system in the respects in which you're interested, the better a model it is. And there are whole projects, for example, trying to map neural network models to the brain and setting up a competition to see who can get closer to, with their model, to what the activity of the brain actually looks like. So this is brain score, but there are lots of other examples. And one sort of standard way of evaluating neural network models of, for example, visual areas is by looking at measures of similarity understood as predictivity. right, understood is how well can my model predict the actual activity that I measure in my target system in the brain. So on the one hand, I think this is pretty intuitive. You might think the more similar two things are, the easier it should be to predict features of one from features of the other. On the other hand, it's also kind of a strange way of cashing out similarity. So you might think it's too easy to get good predictivity, right? Sometimes you can predict one thing from another thing, even when the two things are actually really different from each other. So here's an example. The Hasselm Lab has all these studies where they say we're able to predict what's happening in the auditory cortex of listeners based on the activity in the speech production areas of speakers, right? So that makes a lot of sense, right? Like that conforms with my manifest image of how the world works. But it's also kind of a strange thing to say that the same thing is happening when I'm making words as when someone is listening to what I'm saying and understanding what I'm saying. Surely some things are the same, but obviously some things are really, really different. So it seems like predictivity is giving us something, but it's not quite capturing the kind of similarity that you might care about if you want to build a model of your target so as to understand your target better, right? If I build a really good model of the speech production areas, that doesn't seem like a great way of getting me to understand auditory areas or comprehension areas. That just seems kind of strange, like they're obviously related, but they're not the same for scientific purposes. Okay, so this is a question that sort of matters generally. It's not just for comparing brain models to brain data or for trying to understand particular perceptual areas, but just much more generally, you might be interested in thinking about how to compare representations in two different kinds of information processing systems. And this could be useful for a variety of purposes, as was argued in this position paper from last year. So given that it's useful, and given that there's this sort of facial worry about the subjectivity of how you're supposed to do this, there's this question of like scientifically, how should we assess similarity? And people have given lots of sort of different answers. They've asked this question and they've answered it in various ways. So practically speaking, lots of people use measures like RSA. Other people use linear transformations to try to maximize predictivity. There are also sort of stricter measures like one-to-one mapping that maybe work well for some applications and less well for others. So given that there are all these different approaches, which one should we pick? And I guess just for terminological clarity, people refer to these by different things. So like in the Kornbluth paper, they call it similarity, they call them similarity indices. I think Talia calls them linking functions. We've been thinking about them in terms of similarity transforms or similarity mappings. So ways of getting from this one system to another that allows you to assess how different and how versus how similar they actually are. Okay, so to answer this question, you might sort of back up a little bit and ask, what are the candidate ground truths that a similarity assessment should be capturing for you for scientific purposes? So I also ask for audience responses here. Like, what do you think is important here? What do we need? I know some of you have thought about this
I
question.
guess like one-to-one prediction, ideally.
Like,
there is like the model predict exactly what the behavior is like the behavior is doing, ideally. And I guess it sort of represent, right? So it sort of represent the overall structure. It doesn't have just prediction.
Okay, I see. So you want not just prediction, but you want some kind of reason for this for the prediction to be successful. Okay. Yeah, anybody else? Yeah.
Shared history or shared origin.
In order for something to count as similar. So for you, a model could never be similar to a target if they were produced in different ways. Is that right?
Could be, but I feel like memory would be an example. Like making like the identity of a person, like using all of the sort of history and origin of this memory.
What about more specifically, like if we built two different neural network models that both do a good job at, say, image classification tasks, and we want to ask you know, which one of these, if either, is a helpful model of some aspect of what our visual system does. Right, like what
in the same way.
do they fail in the same way? Okay, so they should like capture the same behaviors. Anything else?
So it depends on.
It depends. Yeah, it depends on your goals. Okay, I completely agree. So, so here are two ground truths that I came up with that I hope are also relatively uncontroversial. So one thought is, whatever you think similarity is, for the purposes of scientific modeling, where you want to build a model of, say, how the mouse brain works, or you know how the primate visual system works, it ought to be the case that what counts as the same, that ceiling is defined by how similar different members of that population that you're interested in are to each other, right? So you shouldn't ask of a model that it be more similar to its target than two members of the target population are to each other. That's one thought. Like that should be your baseline. And a way of making that baseline concrete is, can you identify the same brain area or the same functional activity in different animals? Right? If you're looking at the same brain area responding to the same stimuli, your similarity map should be such that it says these two are basically the same. Under the same conditions, same species. Yeah. Same population. Yeah. And the other thought, which I hope is also not too controversial, is that we should be able to capture genuine functional differences. So it should be able to tell that things that are the same are the same. It should be able to tell that things that are different are different. And by functionally different, I mean, you know, it should be able to distinguish members of different species from each other, but it should also be able to distinguish different kinds of activity within the same animal. So like early vision versus late vision, it ought to be able to distinguish you know, what's going on between B1 versus B4, for example. Okay, does anyone object strenuously to those criteria? Not yet. Holding your fire till the end. Okay, so I think this might remind you of something else that that is kind of a central question in the kinds of neuroscience that I've been thinking about, and that is, what are legitimate ways to extract representations from brain activation? So this is another debate where you might think, well, there's sort of two kinds of goals that we have that we need to balance against each other. Like one is we want to find all the representations that are really there. Let's say I have a bunch of brain data and I want to know what in this brain data is actually functionally relevant for the task or the capacity that I'm studying. So on the one hand, you want your way of measuring or your way of sort of trying to find the representation to be liberal enough that you can find all the representations that are really there, even if they're not super obvious. On the other hand, you don't want to throw a dead salmon in your MRI machine, do a bunch of sophisticated data analysis, and come out with functional activations, which is what this poster is from. That would be sort of doing too much work and finding things that aren't really there, right? You want to find this balance where you want your data analysis method or whatever it is that you're doing in order to pick out sort of the relevant activation as functionally important to be flexible enough that you get the things that matter, and but not so flexible that you find things that aren't really there. So just as with similarity, you want to be able to have a mapping method that's flexible enough that you can see that things that are really similar are similar, even though there might not be an obvious one-to-one mapping, even though they might not look similar at first glance. But you also want it to be strict enough that you don't think that things that are actually quite different from each other, you're just able to force one to do a good job of predicting the other because you put so much into your mapping function, you've made it too expressive. Okay, so what's the answer, I think, in the representation case, something I talked about in a 2022 paper called Putting Representations to Use, is that you should just look at what downstream processes do, right? You should look at what parts of some activation downstream areas of the brain are actually sensitive to. What parts of the signal do they actually use? That's a good way of picking out what parts of the activation are actually functionally relevant. And so similarly, in the case of assessing similarity, you should ask, well, does the downstream area, whatever it's doing, care about the difference between these two activations that you're trying to compare? If it doesn't care, then consider them to be similar. If it does distinguish between them, then consider them to be different. So there's just one strategy. If all comparisons of similarity are similarity from a perspective, and we worry that that might make things subjective, well, then you should prioritize a particular perspective, and that's the perspective of whatever's actually using the thing downstream for the purpose that you're studying. So you should look at how downstream areas respond when you're comparing upstream areas. So I just want to mention a project by Imran Thabani, who's a grad student who's been working with me, and Dan Yeamans, and he's been doing some really interesting work on a project to construct a similarity transform that satisfies these criteria, that's both flexible enough to allow for high predictivity and sort of specific enough, narrow enough that it does a good job of separating models from each other. And basically what he's found is that if you use a linear and nonlinear mapping, that's kind of inspired by looking at what a biological neuron might do when looking at its signals, then you can get higher predictivity without sacrificing separability. So the intuition is that you can sort of fail to distinguish two things that are really different in two ways, right? One is that if you have a mapping that's too liberal, then everything sort of looks the same and you can't tell them apart. But the other way you can fail is that if you have a mapping that's too strict, it will say that everything is really different from everything else, right? And so you won't be able to tell which model is worse in a way, because it's going to say that everything's equally bad when compared to the target. So you want something that's in between. You want something that's able to just see the similarities that are really there. And if you're interested in that project, I'm happy to talk about it more in Q&A. So let me just wrap up. I thought that I tried to raise this question of what we should think about when we're thinking about measuring similarity, and especially functional similarity for understanding a particular capacity. And the answer is basically, even though it's always from a perspective, there is a privileged perspective that we should care about. And that's the perspective of whatever the rest of the brain or whatever the rest of the system more generally is doing with that activity that you're interested in. And when you think about what the brain is doing, you might think about particular kinds of transforms or linking functions that correspond to reasonable models of what downstream areas are doing, and use those directly as your similarity mapping or your similarity transform. And this is a kind of pluralism about what the right transform is to use. So it might be that there isn't a single way to measure similarity across different brain areas or in different contexts. It depends on your purposes in trying to assess the similarity. So that's pluralism. It says there isn't a single way, but it's not arbitrariness, and it's not this sort of unscientific subjectivity where it's like, well, I think these two are more similar, and that's my opinion, and you can't argue with me, right? You ought to be able to make specific what your commitments are when you choose your particular linking function or similarity transform. Okay, that's it.
All right, our comments will be from Talia Konkol, a professor of psychology at Harvard University.
Better way to clear that.
I'm trying to. I can't find
No
it.
maps for you.
All right, I think we're stuck with it.
That's all right.
Okay, go ahead.
All right. Thank you, Rosa, for that talk. Just to summarize what I think some of the main points were. The first was the general issue. Similarity is fraught. It is at best context dependent, to which I'm like, hard yes, totally true. It's actually kind of surprising how far we've gotten with unguided similarity judgments on triplet tasks that give all kinds of structure, given how insane the problem of like context is. So that's a separate line. Where she went next, I think, is the specific case of this, thinking about DNN model layers and whether or not they have similar representations to brain areas. And the case she made was that this is true if the resulting representations are used in the same way for the next stage of processing or for behavior. And to this I go, actually, I genuinely agree. I think this is probably correct. However, I think fleshing out what this actually means is tricky, and then seeing if it's actually viable is trickier. And so I'm going to propose one terminology that I think will help articulate the tension between what we do and what Rose is advocating we do. And second, provide a possible way forward that's maybe not exactly this, but a proxy for this goal. So the first is I want to introduce this distinction between representations with and without a capital R. Putting my philosophy hat on. So I think Rosa's advocating for what I have always thought of as representations with a capital R. They aren't just an encoding of information. It's an encoding with a functional role. It is doing something. It is mattering for the system in the way that it's supposed to be representing a thing. So the representational capacity with a capital R only exists when the content is functionally used. And this sort of shows its head, rears its head in the issues of when we say decode from category selective areas. A common issue and debate that's come up is, hey, it turns out when you make measurements in phase selective regions, you can actually decode whether a house is present or not. And thus we make a lot of concern. Is that area actually representing houses? What if it's not used by the system to detect a house? So then it's not functionally relevant. So it doesn't count as representation with a capital R. That would be the argument, because it must be functionally used by a later stage system for readout representation awareness, something like that. But readout commitments are hard to measure, to understand. I think the idea of just use the next brain state is like belies deep complexity of like, does that assume serial processing? What about modulatory? What about loops? Like, I don't know how to hash that out. And I think we struggle with this and have been struggling with fMRI decoding. So then that brings us to representation, the soft representation. And this is one that's just a commitment to an encoding format. It's got a basis set. If you want to think about pixel representation, pixels are the axes and images land somewhere in the space, or a Gabor jet representation, or a V1 representation. That's just an assertion that the neurons I happen to measure from V1 are my basis set, and images activate each of those to some degree, and that is a representation. And this is safe. It's just measurement. It's true in some measurement-y kind of way, but it doesn't actually get us to representation with a capital R, which is what we want. And so there's a sneaky balance with us sort of measuring representations and trying to claim capital R representations. And comparing representations is really easy when the basis set matches. I can take two pictures, if they have the same, pixels, I can just subtract them. It gets tricky when the basis set is different, when there's an uneven number of neurons, or when when you're changing systems, even between brains, right? Like when there's not a one-to-one match, we're like, okay, now what? And this is where I think we've developed some linking methods, kind of empirically and out of necessity, which sneakily have implicit readout assumptions, which we haven't necessarily thought as deeply about as we could, or those are just starting to emerge. So one of the standard ones is classic RSA. I mean, I remember when this paper came out and Nico figured out how to measure and correlate monkey IT with human IT on the same set of images, and classic RSA was opened up huge frontiers. But on the other hand, it makes some commitments implicitly for what we mean the representation with a capital R really is. It assumes that tuning directions are not the relevant information carrying signal, and the population level match between this set of neurons and this set of neurons are like the same in some important sort of coverage kind of way. It assumes maybe you have a readout to access to the full population, and even the distance metric itself, correlation, cosine distance, all make subtle differences into what you think the information carrying signal is that matters for representation with a capital R. Same with encoding models. So I should probably not go into too much detail, but say you pick a single unit. Now you're saying, I think this unit's tuning really matters. So that's like a move away. So saying tuning matters. But the standard approach is let's fit any combination of tuning across the whole layer of deep neural network models, which is sort of like a commitment saying, well, tuning matters for the brain, but it can be arbitrary in the model. Do we really mean that? Shouldn't tuning matter for the model too? So these are just standard approaches. And I think it's because we actually lack deep agreement on what the information carrying signal is in these complex information processing systems. So a question back to the philosopher is just use the same operations as the next part of the brain, assume something that I don't know how to measure or even quite comprehend. Is it serial? What about loops? Is this really a viable concept? Is it practical even if we could measure everything? So how do we get from representation to capital R representation? And one possibility is, well, let's just try and get to as close to a one-to-one match as possible. Because if it one-to-one matches, then we're good. However it's used, it matches one-to-one, we're set. Okay, so this gets to a deeper question though, which is how do we want to think about how AI models are related to brains? And one idea is to think of these as models of the neural system, where there's some direct correspondence and you want to basically find this goes with this and this goes with this and these are the connections, and you just keep adding biological detail to keep accounting for brain data. And I think this bottoms out in the limit at build a one-to-one in silico brain model, because any relevant biological detail is in scope and now you're building an in silico replica. But another way to think of these models is more like model organisms, like we study mice and monkeys and flies and AlexNet models. And we do that not because we think they are an exact model of the human brain, but because they do something interesting and they use similar information processing systems. And we study them maybe to understand how they work and gain insight into how our brains might work. And this I would also call safe. And it's a playground where we can start to link mechanism with capital R representation in these models. Just going, well, this mechanism matters for the representation in this model. And it may or may not be like how the brain does it, but at least we can get a handle on it where we have deep control of how the information processing goes. We know exactly what the next stage is, et cetera. So maybe what I would offer to Rosa, a change of the goal from exactly match the next stage to discover the principles of readout or information transmission. And some intuitions on this front is studying these ReLU networks. The ReLU has a lot of juice in it. It's a real deep insight into what can pass to the next hierarchical layer. We often say you can rotate the axes, but once you pass through a ReLU, now if you've rotated those axes, they're not the same information isn't getting through the hierarchical layer. So, classic RSA, which discards those tuning axes, is going to miss that. So we think maybe what these networks are really doing is something like positive information signaling as the information carrying signal. And a related sort of corollary of thinking about this is let's make some commitments about the linking function. It's not just an arbitrary mapping, but like, let's think about how information is flowing in each of these systems and make our constraints match those. So we've been advocating for something like sparse positive constraints, which is like, try and make these as aligned as possible. Also, don't flip the sign because the network can't use the negative sign. It won't make it to the next layer. So don't give your encoding function more information than the network itself has for the next stage. And I think people are just starting to work these out, and we're still as a field kind of figuring out how to do this, but I think it's in the right direction. And I would advocate that studying the models in and of themselves with simple knowable information flow might actually give us some deeper handle on what counts as representation with a capital R, which we can then go test in the brains and see if that's true. So in sum, I totally agree. I think moving toward representation with a capital R is what we should be doing, but I think how is tricky. And I've made the move that maybe in trying to measure the neural next step might be too hard, or I don't know what that looks like yet, but maybe understanding how these simpler model systems work will give us some ideas. And with that, thank you.
We have time for a couple questions for either Rosa or Talia. Again, the microphone is in the middle. Ian, go ahead.
Hi, Rosa. That was great talk. So in solving the problem of similarity by looking at same use, it looks like the term similarity is basically being reintroduced at that level. So do you think that it does nonetheless kind of narrow the problem down by, after all, what makes a use the same use?
Yeah, so by use, okay, sorry. So by use, I mean something like if you think of what's happening downstream as a transformation, then you just want to know, do they get mapped to the same output by that transformation? And right, and what counts as the same output, right? It does seem like you have to have another assessment of that. But I was thinking if you, in the limit took the whole, rest of the downstream system, whatever happens next, whatever criteria you use for measuring behavior in the end, use that same criteria, right? So it is going to be relative to your purpose in doing the experiment and trying to assess the similarity, but it's pushing it to there instead of saying you have to have some independent objective means of assessing similarity.
So I wanted to ask, in terms of our deep neural networks either being models of, or even a representation of, a model organism kind of framework, how do you deal with the fact that almost certainly we're dealing with an ill-posed problem? And I mean, just by definition, so many different organisms have solved it in so many different ways. It's an ill-posed problem. So how can it be either represent either a model of the visual system or one that is a model organism, given that it's nonlinear function approximation, not nonlinear function, like we're not actually getting the nonlinear functions.
I confess I understood maybe 75% of the question, but I'm gonna go with what I think you're saying, which I think we get to make the move. I'm gonna just call it a model organism and stand my ground on that because it takes, it's a function, it's a simple one. It takes some input and it gives you an output. It doesn't have recurrence, it doesn't have goals, but it has so in a way, it's a function mapper, but I still think it has principles of how information flows across stages that are going to give us insight into how the brain works, and already has. And so even though it's like really not complicated enough to be close to a model of the brain in any deep way, it's not even biological and like, mice and monkeys. I think at an information processing level, there are real principles that have proven to be useful. And so while it continues to be useful, we get to keep making that move. But it's a safe answer. And that's where I stand, a safe ground. Yeah.
We have time for one more.
Hi, thank you so much for the talks. I found them really insightful. If I understand you correctly, Rosa, you're I feel like there's somewhat of an analogy to behaviorism, kind of you looking at what sort of processes come out of whatever black box dimensions of similarity we're using and staying relatively agnostic to the nature of the representation or the content of the representation. And Talia, it sounds like you want to investigate that more, that's sort of like what is inside the black box, and well, the sort of like the usage of the representation can be useful metric for constraining what the content can be. Like looking into the content itself is ultimately perhaps more productive, if I understand correctly.
What I got this. Okay, well, I guess people who know me will know that I think that behaviorism is kind of underrated. That being said, I think this whole project of trying to compare activations within models and brains is, trying to look inside the black box and trying to see in virtue of what is it that this particular behavior is produced. So I agree with everything that Talia said about little r representation versus big R representation. It seems like big R representation is what we really care about for psychological explanation and for trying to align the manifest image where we think in terms of having mental states and so on with the scientific image where we're measuring like things that are happening in the brain biologically. But I think in order to do that measurement, you have to think about how it connects up to behavior, right? If you don't think about how it connects up to behavior, then all you have are just these activations that are completely meaningless. I don't think Talia and I disagree so much in that respect. It's true. I agree.
All right, thank you so much, Rosa and Talia. So our final speaker is Tina Rosenquist, who's a postdoctoral fellow at Dartmouth College in the Society of Fellows and in the Department of Philosophy. And their talk is titled Seeing with Color, Psychophysics and the Function of Color Vision.
Thank you. Can you hear me okay at the back?
Yes.
Okay, cool. Let's see if I can, yeah. All right, so I'm so excited to be here, a little bit intimidated, but mostly excited. So I'm going to be talking about the function of color vision and what psychophysics can tell us about that. And the idea that I'm defending is that the color visual system is a perceptual enhancement system, and it's not a color detector or surface spectral reflectance detector. And I think that we should accept this idea because it's the best explanation for the relevant sort of psychophysical data. So I'm a philosopher, so I'm going to give you an argument, but the argument is only there to structure the talk. So in the first part, I will motivate the idea that we should go for that conception of the function of color vision that best explains the kind of perceptual phenomena that characterize our ordinary color perception. In the second part, I will give you the relevant alternatives, which I call seeing color and seeing with color. In the third part, I will go over the relevant sort of phenomena. In the fourth part, I will make my case for the claim that we should go for the seeing with color conception, or the idea that the color visual system is the perceptual enhancement system. Then I'm going to go over a couple of objections, hopefully if I have time, and then I will conclude that yes, indeed, we should think of color vision as being there for perceptual enhancement and not for color detection or SSR detection. Okay, so philosophers who work on color and color perception ask questions like, what is color? Where is it? Is it real or is it illusory? When our color experience is correct, and what kind of knowledge does color vision primarily ground? And most philosophers who are working on color today see themselves as doing empirically informed philosophy. But there are a couple of different ways of doing that. So you might start from the armchair with the traditional methods of philosophy, consult your intuitions or do conceptual analysis, build a theory based on those methods, and then see what that theory has to say about empirical findings. I think a better way and more genuinely empirically informed way of doing philosophy of color is to bracket those intuitions to the extent possible and let the data guide your inquiry. So I call this approach empirically guided. And I think if we go for this empirically guided approach, a good way to start is by asking about the goals or the aims or the functions of color vision. So do task analysis. And there's a little bit of debate about what kind of data is relevant to answering this question. So some philosophers think that neuroscientific evidence, we shouldn't really worry about that. Others think that comparative color vision, visual ecology in general is not relevant, but virtually everybody agrees that psychophysical data is relevant. And that's why I'm focusing on psychophysics in today's talk. So now we have arrived at the first premise of the argument, which is that the conception of the function of color vision that best explains the kind of data investigated by psychophysics is the one conception that we should adopt. Okay, so moving on to alternatives. I was also asked to use pictures and colors and that's why okay, I'm not going to motivate this idea very carefully at this point, but I'm just going to suggest that there are two relevant alternatives. These are the alternatives that you will find in the philosophical literature. So the first option is what I call seeing color, and this is the idea that color visual systems are surface spectral. They are color detectors. So the function of color vision is to detect or track and represent fine-grained stable colors of environments, digital scenes and objects. But the philosophers who go for this view usually identify color with surface spectral reflectance or think that it's somehow straightforwardly dependent on that. So if you don't want to accept the idea that we see color, you might still be kind of related to this conception. You might be willing to accept this conception if you think that the color visual system is solving for surface spectral reflectances. This is the mainstream view in philosophy, which might surprise some of you. The alternative to that view is the idea that I call seeing with color. And this is the idea that the function of color vision is just to enhance our perceptual interactions with our environments. So what color vision is trying to do is to allow us to better see things other than color. So things like objects, properties like brightness, and relations like distances and spatial layouts in general. All right, so now the psychophysics, intimidating part. So I don't need to tell you what psychophysics is, but psychophysics of color investigates how changes in the physical stimulus properties affect our color experiences and judgments. And according to the third premise of my argument, the relevant sort of perceptual phenomena that characterize our ordinary color perception are approximate color constancy, which is the relative stability of the perceived colors of targets across lighting conditions, and color induction, which is the effect of neighboring surfaces on the perceived colors of targets. And I think that these are the relevant phenomena to think about because they're systematic and they're pervasive. So whenever we're out in the wild perceiving, our perceptual experiences of the colors of our targets tend toward constancy, but they're also systematically influenced by the spatiochromatic context in which we view them. These phenomena also seem to pull in opposite directions. So when we think about color constancy, it seems to suggest that at least one function of color vision is consistent with the stability of perceived color, whereas color induction suggests that at least one function is consistent with the variability of perceived color. So even if we were to add some other phenomena to this list, it wouldn't really change the basic explanatory task, which is to somehow reconcile these different tendencies. Okay, so approximate color constancy, decades of research on that, we know that perceived color correlates better with surface spectral reflectancies than it does with the spectral properties of the light incoming from the target. So I've borrowed an image from David Foster. Here, the target surface is a little bit of flower. You see the white arrows that are pointing at them. So when we view, for example, flowers like these in different lighting conditions, the spectral characteristics of the light entering your eye can be very, very different, but our perceptions of the colors of those flowers are kind of reddish in most lighting conditions, normal lighting conditions, not in monochromatic light rooms like last night. So pretty early on, we figured out that there's two kinds of constancy, really. There's the constancy of perceptual judgments about the way things are. So that's when you ask your participants to match surfaces as if they were cut from the same piece of paper. And then there's the constancy of phenomenal appearance, so the actual fine-grained hues that are presented to you in your visual experience. So we know that the constancy of perceptual judgments is higher. Constancy of phenomenal appearance is much lower, but the conclusion that we can draw from those decades of research is that constancy, any kind of constancy, is approximate at best. Okay, and then simultaneous color contrast is the first type of color induction I want to talk about. So this is the effect when you have the perceived color of a target shifts away from the color of the inducer of the neighboring surface. These effects are strongest when we have targets that are embedded in uniformly colored surrounds, especially when those surrounds are highly saturated. So in my little demo, I have these photograph icons that are placed over differently colored backgrounds. And if you get the effect in the top row, the color of the icon goes from kind of brownish to more yellowish to more greenish. And then at the bottom, if you get the effect, it's kind of pinkish and then achromatic gray, and then maybe slightly purplish. If you get the effect, but if you don't get the effect, I'm sure you've all seen demos of simultaneous color contrast before. So these effects are very common and they're very easy to elicit, even for philosophers. And we have reason to think that simultaneous color contrast occurs whenever we have targets that are embedded in these uniformly colored surrounds. The other kind of color induction I want to talk about is color assimilation. So this is the opposite effect. So the perceived color of the target shifts closer to that of the inducer of the neighboring surface. Here's an image that I borrowed from Akiyoshi Kitaoka. So we have red circles that are overlaid by colored lines. So the red appears differently, or it's a different red appearance that you get in the two cases. Color assimilation is also common in daily life. It's strongest with variegated surrounds or more complex spatial patterns. Lots of things affect the strength. Luminous contrast between the target and the surround is one factor. Another factor is the color of the surround. So in this one interesting study, it was found that green surrounds are less likely to induce assimilation. And the authors of the study suggested that that's because in our evolutionary environment, it would have been very important for our ancestors to be able to discern edible plant material against green foliage. So assimilation with green surrounds would be detrimental to that task. Assimilation also often occurs within clearly defined boundaries. So another illustration that I borrowed. So if you're far enough away, you will probably get the effect. So this is the black and white picture, which is overlaid by colored grid lines. So if you get the effect, the colors of the grid lines spread to cover the enclosed areas, and it might look like a normal colored photograph. All right, so now best explanation. Starting with color constancy. So just to remind you, seeing color is the idea. The function of color vision is to track and represent those stable, fine-grained hues. So now it looks like seeing color is a pretty good explanation for color constancy. Because if our color visual systems are tracking SSRs are stable, there's an explanation. Michael Childs, a philosopher, has suggested that this is the simplest, most straightforward explanation. David Hilbert, who's another philosopher, at least in '92, thought that it was the only plausible explanation for color constancy. And I think this would be true if color constancy was better, if it was perfect, or near perfect even, but it's not. And the fact that it's not, I think, should give us some pause here. It's not at all clear that color constancy is evidence for the idea that what our visual systems are doing is tracking surface spectral frequencies. Seeing with color, which again is the idea that color visual systems are perceptual enhancement systems that are not tracking SSRs, can actually explain approximate color constancy pretty well. Because what approximate color constancy allows us to do is to recognize objects and recognize object properties like brightness better and faster. Masvida Chirimura, who's both a philosopher and a vision scientist, has suggested that maybe color constancy has more to do with maintaining these stable relations between the experienced colors of objects across lighting conditions. And we are very good at that. We are very good at telling when there's a change in the chromatic appearance of the scene. We can attribute that change either to changes in lighting conditions or changes in the material properties of the objects in that scene. So this might explain some of the color constancy research. A lot of the studies may have actually measured relational color constancy and not color constancy proper. But it's also likely that there's some discounting of the illuminant going on in our visual systems. So our visual systems are doing something to kind of ensure that bananas look yellow in different lighting conditions. But note that this does not entail that the visual system is detecting or tracking SSR. It might discount the illuminant just to make it easier for us to recognize properties and objects. All right, so then color induction. Seeing color really struggles to accommodate these effects, because if the function of color vision is to track and represent those stable, fine-grained properties of objects, it really doesn't have any explanation for why changes in the spatiochromatic contexts in which we view those targets systematically bring about changes in the perceived colors of those targets. Quite often philosophers suggest that induction is just, these are just illusory effects. We don't need to worry about them because it's just, oh, I like this response, because they're just instances of color visual system failure, but there's no good empirical reason for this kind of differential treatment of constancy and induction. So there's nothing in the data that tells us that color constancy is a clue to the function of color vision, and color induction just reflects color visual system failure. Also, if color induction effects turn out to be useful for perceiving animals, then that usefulness is going to be merely accidental in this picture. All right, so seeing with color doesn't have any trouble accommodating and accounting for color induction, because what color induction seems to help us do is to segment visual scenes into separate object components. So simultaneous color contrast allows us to see objects as separate from their backgrounds, whereas assimilation allows us to perceive targets as integrated wholes, even if there's some surface variation. Seeing with color also gives us a nice unified account of constancy and induction, because some degree of constancy is useful for object recognition and property recognition, whereas induction is useful for scene segmentation and so on. So if the function of color vision is to be this general sort of perceptual enhancement system that allows us to better perceive the spatial layouts of the environments in which we're in, and allows us to better recognize objects and object properties, all of this makes very good sense. So this is the fourth premise of my argument. Seeing with color best explains all these relevant phenomena. Okay, so I'm only going to consider a couple of objections. I think that these are the strongest objections to what I've said, so that's why I bring them up. First one is kind of challenges the idea that seeing color and seeing with color are the relevant alternatives in this debate. So you might think that actually we should go for a hybrid conception. We should think that the function of color vision is both to track and represent those stable fine-grained colors and to function as a sort of a general perceptual enhancement system. My response to that is going to be quick. When we have two conceptions that explain the same phenomena, have the same explanatory power, we should go for the simpler one. And in this case, the simpler conception is seeing with color. We don't need to bring in the idea that the color visual system is tracking SSR. That is unnecessary. There's also the issue of conflicting verdicts on the question of success versus failure, because in a lot of cases, when we are evaluating on color experiences for correctness, seeing color is going to suggest that those experiences are incorrect just because there's so much variation in color perception, whereas seeing with color is often going to suggest that those experiences are correct because they're successful. They allow us to better perceive our environments. Another objection that I will consider briefly attacks the last premise of my argument. So the idea that seeing with color is the best explanation for the phenomena considered. So I haven't actually seen philosophers make this point, but I think they should. If they go for seeing color, I think they should say that color induction merely reflects the mechanisms by which color visual systems compute constancy, because there are reasons to think this. I mean, we know that the same neural populations might be involved in both constancy and contrast computations and so on. So the idea is that we can ignore induction because induction effects only tell us about how our color visual systems compute constancy. That's the objection. That's the idea. My response to that is that the evidence really isn't clear, so we don't know the exact relationship between constancy and induction. But even if induction mechanisms were involved in constancy computations, that doesn't mean that that's all they do for us. So it's a little ad hoc to assume that contributions to constancy computations explain the existence of those mechanisms. And also the independent usefulness of induction is still going to be accidental in this picture. Okay, so we have arrived at the end. We have arrived at the conclusion. So I'm just going to summarize briefly. Seeing with color, or the perceptual enhancement system view of color vision, is the conception that we ought to adopt if we want to do philosophy in an empirically guided manner. This conception best explains the perceptual phenomena investigated by psychophysics. The rival conception relies on some kind of previous theoretical commitments or intuitions or assumptions, and possibly also ad hoc reasoning depending on how you want to deal with induction. And it also cannot explain the independent usefulness of induction effects. I think that the case for seeing with color can be made stronger if we bring in evidence from neuroscience and visual ecology, but for now, this is all I've got for you. Thank you very much.
Thank you so much, Tina. Our final commentator is Bevel Conway, who is a senior investigator at the National Eye Institute and the National Institute of Mental Health.
Do I push this one or this one? You'll the right one. No. All right. Okay. Yeah, thanks to the organizers and to Tina for a great paper. She nicely motivates this question, which I'm sort of paraphrasing as what is color vision for? She says that neuroscience hasn't been useful on the question, and I'm flattered that she uses me as her example. I'd like to try and persuade you that neuroscience is useful, and if I'm not successful, then hopefully I can persuade the philosophers to help me out. Okay, so as we get started, I think it's worth asking ourselves what the question begs. So it seems to me that it presupposes that color vision is some kind of discrete thing. The question also seems to reinforce a common intuition about how the system operates, namely that it's a kind of domino cascade whereby physical signals are emitted from things in the world, transduced by the retina, and then processed by the brain to ultimately trigger behaviors such as perception or reaching. In this framework, we somehow miss the crucial question, what is color? So pulling back, you might recognize this from last year, we can see how misleading this intuition of a domino cascade is. So the woman is dancing, and as her eyes, head, and body move, what she sees changes. Her body movements, what we have called her response, in fact precede the stimulus. They are what determine the stimulus. In a very real sense, we are all creating the sensory environments
we each experience. So here we are. Now, what am I supposed to do? It says, don't allow. Animations happen. So in a metaphorical sense, vision is touch at a distance. So our brains reach out to restructure the world through eye and body movements and the physical actions we take upon the world. We adorn ourselves with colored lights, pigments, and clothes. We make paintings, and we radically alter the world to create the physical spaces that we inhabit. In every direction is something a human being has created and colored. The domino cascade intuition can't be right because our actions construct the sensory world. And since the brain controls our actions, the brain makes the sensory world what it is. This idea follows from the reflex arc of psychology proposed by John Dewey in the late 19th century before neuroscience was carved off from philosophy. Science teaches us that this co-construction of response and stimulus likely happened also in evolutionary time, in a process we could never know anything about from intuition. Primate color vision evolved to detect fruit pigments, and fruit pigments evolved to match primate color vision. So contrary to intuition, we don't reach because we see because we need to reach. Introspective philosophy might provide us with a user's manual for the brain, a guide to experience, but it isn't going to give us a construction manual on how the system works. For that, we need data. So the answer to the question, what is color for, very much depends on what kind of manual we are after. Tina attacks the idea that the goal of the color vision system is seeing color with the astute observation that color constancy is not perfect. To recap her argument, it goes something like this. If seeing color were the goal, then color constancy would be perfect. Color constancy isn't perfect, therefore seeing color isn't the goal, and the goal must therefore be seeing with color to detect objects, recognize friends, find mates, navigate, and so on. I agree with her that the colors of objects are not immune from lighting conditions. This obviously became clear from the dress, if it wasn't clear before. Some people see the dress as white and gold, others see it as blue and black. These differences might be explained by different priors about the lighting of the color, warm sun versus blue sky. But regardless of whatever theory you might have, there is no doubt we have color experiences. And these experiences are so meaningful that when we disagree about them, they make international news. Like Tina, I broadly subscribe to the adaptationist view that evolution does a pretty darn good job. But I think this assumption should bring Tina's argument to a different conclusion, for we do see color. So seeing color must at least be partly what color vision is for. As Tina argues, the way forward must involve data, and I'd like to vouch for neuroscience as an especially useful way of moving us beyond the limits of intuition. So here are 3 examples. The first is the neurophysiological discovery of chromatopic maps in the globs of E4. These maps recover perceptual color space, which is evidence that we do see color. They also provide evidence that favors Hume's famous speculation that we could discriminate shades even if they were missing from our experience. Then there's magnoencephalography data. That discovery shows that perceptual representations of color give rise to semantic representations, but not the reverse, which speaks to the distinct natures of perception and knowing about color. And finally, there's functional magnetic resonance imaging data, a discovery of a vast network of color-biased regions in the ventral stream. This is in parts of the brain implicated in so-called high-level vision, which provides hypotheses about the mechanisms that support the full host of color-related behaviors, including grouping, categorization, memory, social cognition, social communication, reward, and so on. So other neuroscience data strongly suggest these bits of brain acquire their functions through experience and development, the neuroscientific evidence of Dewey's reflex arc in action. But I think it's ultimately powerful. I think what is ultimately powerful about data is that they allow us to imagine things we couldn't imagine if constrained by intuition. And hopefully they will excite philosophers to help us understand what the data mean. For me, color can only be understood at the nexus of the physical world, brains, and evolutionary pressures. Color becomes an adapted and an adaptable system that enables a vast diversity of behaviors, a diversity that demands many more than one answer to the question, what is color for? The answer isn't seeing with color or seeing color, it's both. And if neuroscience is our guide, there's probably many more answers too. Thank you.
Thank you, Tim and Bill, for those really wonderful and like moving talks. Let's open up for a final round of Q&A.
Very nice talk and even better comment, I would say. So I'm also tend to believe that there is not one function, there are multiple. And you consider this as one of the objections, and you appeal to Occam's razor in defense that there is one simplest explanation because of Occam's razor. I would like to challenge the relevance of Occam's razor in evolved systems. The brain is a patchwork of all kinds of circuits. There are different pathways, and it's kind of a hodgepodge that a lot of it was conserved, a lot of it was kind of added on. So it is not a simple parsimonious system. It is a patchwork, a lot of complexity, a lot of redundancy, a lot of messiness. Why should Occam's razor be any guide into what's going on there?
Thank you. And this also allows me to respond to Evan a little bit. So, I think that seeing with color is actually the view that there are multiple sub-functions for color vision. And it also kind of accords very well with Beville's idea that color vision is not a discrete thing, because even if there's multiple subsystems that are kind of doing their own thing and their outputs are somehow combined in conscious color experience, that is consistent with seeing with color. It is not consistent with seeing color. It is not consistent with the idea that color vision is a single function. So that's the thing that I'm attacking. The hybrid view would bring in the idea that in addition to color vision playing all these various roles, it's also tracking SSRs. And I don't think we have good empirical reason for thinking that. I think chromotopic maps and perceptual color spaces and all of those things we can accommodate within seeing with color picture without having to bring in the idea that we are detecting colors out there. I think the issue between me and Beville is that we understand the word seeing differently here, because I use it as a kind of a success term. We see color when our color perceptions match those colors of objects out there. So it's a success term. For you, it seems to be about experiencing color. I have no problem with that. It's incredibly useful for us to have color experiences because it allows us to recognize objects better. So thank you for that.
Yeah, so thank you so much. I really love this project. So one question I have is similar to the multifunctionality. So there's general theories in philosophy of biology where they're very permissive about the multifunctionality. So you could have a lot of different activities of the system contribute in different ways. But related to that, it sounds like you have kind of too high of a bar for what would count as a seeing color function. So it could be that in certain cases, all you need is just that discounting the illuminant and focusing on the surface, which is going to be the task relevant property in a lot of cases. And just having the approximation being good enough to perform whatever task you want is going to be enough to contribute to the survival and reproduction of the organism, which is going to be enough to get the function description going. So I was thinking that this happens a lot in spatial perception too, where you only need like ballpark estimate of the room to navigate it or something like that. So I was just wondering why I think that you need such a high bar to get the function description going.
Thank you. Great question. I think the empirical motivation for seeing color is often color constancy. So I'm just trying to pull the rug out from that reasoning, because it would be a good reason to accept seeing color if color constancy was better. But because it's not, we need some additional reasons to think that, and we don't really have those additional reasons, at least no additional empirical reasons. We might have intuitive reasons, but also intuitions and conflict, and we probably shouldn't really rely on those very much when we philosophize about perception and perceptual properties.
So I think I agree with your conclusions, but I'm a little bit worried, like other people, about the argument involving simplicity to get you there. So it seems like, maybe we should use Occam's razor when we're positing entities and when we're positing rules. But it seems like for something like evolution, there are probably lots of selective forces acting on lots of things and pulling in slightly different directions at different times. So it would be really surprising if there were a single function for anything. And I wonder why you think it would be better to posit a single function rather than thinking of functions as kind of like a overlay on this like massive data that's trying to simplify it and pick out some aspects as being more salient than others, and thereby being open to there being a multiplicity of functions.
Yeah, so I'm seeing with color is the idea that there are multiple functions. So I just don't think that we need to bring in the idea that we are tracking stable fine-grained colors of distal objects to that picture. So if that adds nothing to the explanatory power of the view, why should we go for that? Why should we bring it in? We don't have any empirical reason for that position, so.
So you might think it organizes some of the data where it looks like these were things that were selected for producing color constancy in the service of seeing the color.
Yeah, so
like a hierarchical sort of view of how the functions are.
yeah, I think that's probably how it worked. We started probably initially. I mean, I shouldn't say anything about that because I don't really know. But I think probably initially color vision was just evolved to help us perceive objects and to defeat Q ambiguity and things like that. And then after a while, maybe color constancy evolved because approximate color constancy evolved because creatures like us need to recognize objects and object properties. But I don't think we need to bring in the idea that we're tracking SSRs at any point of the story. Yeah.
One last question.
Yeah, that's great. So, color constancy is not optimal. But do you think that it requires that it's not optimal in precisely the ways that allow it to perform those different additional functions like helping with object segmentation?
Yes. Yes, I do.
Great.
Okay.
That's all.
Okay.
Kevin, I think probably it's worth coming back to, flipping the equation around. The argument seeing with color to dismiss seeing color requires that all of the functionality that seeing color confers on us can be obtained by some other route. And that is not true. Seeing color allows us to do certain things that you cannot do with other sensory cues. And that is why we have evolved an ability to see color. And it's why seeing color is an inextricable part of what the objective is of the color vision system.
Yeah, or maybe simply like, can we see with color without seeing color?
Okay, this kind of touches upon the unconscious perception debate. So yeah, maybe we can. But I think for most of the functions, sub-functions that fall under seeing with color, we do have to, well, maybe not most, but at least recognizing objects and object properties, we have to experience color. But not necessarily see color in the sense of like tracking something that exists out there.
No, but I think we do, right? A lot of the behaviors you talk about with seeing with color
Mm-hmm.
require recovering stable color signals, right? Being able to account for the variability introduced by illumination so that the pigment, you're talking about ripening fruit, right? So that's actually a stable property under varying illumination, so you can enact whatever behavior appropriately.
So I would say that what is needed for that is just relative stability of experience, and that can be accomplished even if the system is not actually tracking SSR or any kind of stable property. We can have, I'm not sure how color constancy, approximate color constancy is achieved, but it might be achieved by some kind of algorithms that have nothing to do with estimating or computing the the spectral properties of the illuminant, or even if it did that, it still doesn't mean that it's has to do with getting us closer to those stable properties out there. All we need is like relative stability for our color experiences to stay within a certain range that is enough for us to recognize objects and object properties.
That's all the time we have. Let's thank our. So we want to thank Ian, Rosa, Tina, Jeremy, Talia, and Bevel, and all of you so much for being part of this event. Thanks to our sponsors, both at York University, the Department of Philosophy, and Vision Science Applications Program at Johns Hopkins, the William H. Miller III Department of Philosophy and the Vision Sciences Group, and we look forward to seeing everybody next year.
Thank you, that was fun.